everyone. I'm Marc Zyngier. I work with ARM. So it's the last talk in a long series of Spectre-related ones. So I may go quickly through some slides because you've probably bored to death and I'm between you and lunch. So it's not a very good place to be. So the original title was KVM meets the villain, Mitigating Spectre. I've just reworked it to be Mitigating Spectre at the architecture level because, as you know, ARM, although we design CPUs that you have in your phones and maybe one day in servers, we also, and most importantly, define an architecture, and which means we're not in control of implementations in general. And that put things in a slightly different perspective. So a bit of literature, the original Google Zero project posting with variant 1, 2, and 3, which became also Spectre v1, 2, and Meltdown. I'll use both namings over the talk because I'm just massively confused in general. There's this thing called variant 4, SSB. And there's also the ARM white paper, which we published just after the initial Google Zero postings, where there's the official ARM position on all this. Let's define some terminology. So what is an architecture? So the way we define it is that it's the contract between software and hardware. It's a set of rules that defines what is permissible and what is not. You can build things in certain ways, in any way you want, but there are things you can do and things you can't. And that's independent of any implementation, really. Then we have what we call the microarchitecture, or an implementation. So it's really that. It's, we're building some hardware that matches the architecture. And you can do anything you want there, as long as you don't break any of the rules set in the architecture. And now, what is speculative execution? So, as Alex brilliantly explained, is a really good optimization where you can do things before they are actually required, and that allows parallelization to occur in the hardware. And well, one thing Alex didn't say is that you may have to roll back things when you've mispredicted something. And that's where things become a bit, not that good. So with help from Frank Zappa, any good presentation should have a Frank Zappa quote. Doesn't mean this presentation is good, but still. So anything, any place, anytime, any place for no reason at all. And I would add, because something, somehow, somewhere went slightly wrong. And with that, coming back to something slightly more serious is, what is our threat model here? We're talking about KVM. And we assume that a hypervisor is at a higher privilege level as the guest. And we really assume that whatever state we have in the hypervisor is not visible from the guest. Well, the thing is, we're finding out that side channel attacks allows disclosure of those secrets, password keys. Alex, this is my passphrase, my secret passphrase. That's really important. That makes use of speculative execution. One thing to notice is that this is all about disclosing data. You don't modify data. Hopefully, nobody has built speculative rights. Please don't. So I'll go quickly on that one, but the general principle of these timing attacks is that you start with a large-ish array of memory, and you, one way or another, you make sure that it doesn't sit in the cache. And then you try to influence the hypervisor so that it uses one of its own secrets as an offset into this array of memory. And you do that in a speculative way. That becomes tricky already. And at some point, you're able to time you're able to look at the time it takes for you to access this array of memory. back in the guest. And find out, oh, that cache line is much faster than the others. Disclose a tiny bit of information. Of course, the hard part is convincing the hypervisor to use that array under speculation. And that's about it, really. So as far as ARM is concerned, we're looking at 4 classes of attacks. One is Spectre v1, which is about doing boundary check bypasses. The other one is being able to re-steer branches from one location to another. You prime the branch predictor. That's Spectre v2. We have some form of privileged separation bypass. Meltdown, being able to speculate through something where user space didn't have access to. Or this thing called Variant 3A, which we initially thought only affected ARM until we found out that it also affected x86. Who'd have thought? Which is about having accessible system registers. And then things having to do with memory ordering mispredictions, and that's Variant 4 or SSB. And of course, someone will come and combine these things together to create gadgets. We really don't want that. So let's start with the one that is really hard to mitigate, really, Spectre v1. So that's the very, very simplified view. If you want the real thing, please look at the first page of the Google Project Zero blog post. They explain that in really detailed way. But the gist of it is this boundary check here. If array bound is the size of your array, you have an index, and before dereferencing that array, you check, is it in the range, and it's all good. It's good, isn't it? Except under speculation, well, that check can be bypassed for some arbitrary reason. As I said, the CPU can do anything you want in any order as long as you respect the architecture. What can happen is that check can belong to resolve. Maybe that array bound involves actually missing in the cache and having to load something that is really far away. Oh, well, in the meantime, I'm still going to try and perform the access, and bad things happen. So the array can be entrusted, the index can be entrusted, the array can be under control of another exception level. And yeah, again, please read the full thing. It's really interesting. So on ARM, how do we mitigate that? It's a bit complicated. So we want to prevent speculation to go beyond that check of our index. So the way we do it is it's a two-stage mechanism. So we have a way to, which is, it's a cool hack, where we can check that, that boundary so that the CMP instruction here, that you compare your index and your array bound. And then we do a subtract with carry here. So if carry equals 0, then here you have -1, which is a mask basically full of ones. Otherwise, you end up with 0. And what we do here is that we end our index with that mask. The result is, if we ignore speculation for the moment, but if you think of it, the result is you're out of bound, you get something that is 0. You're out of bound, you get something that is actually what you want, what you've been given. So that is good, except we still have speculation to deal with. And that's the role of that CSDB barrier, which guarantees that anything that either depends on a C-cell instruction or use flags would be executed, and there won't be any speculation beyond that barrier. It's a bit of a convoluted semantic, and it took time to come up with that. But that actually works on all existing implementation. So it's the first example of things where we try to do things that we verify that they work on all implementations, which means coordinating with a lot of implementers, people looking at people designing implementations and agreeing on a common semantic. Variant 1 is actually quite difficult to deal with because it affects everything that has a privileged boundary. It's everywhere, including in user space code. KVM is not different from any other software in that respect, which means we need to mitigate it at the API level in our IRO tools. So we've done that in a few spots where we could actually see that it was vulnerable. It's really hard, and we rely on static analysis for that now. If you don't know about it, look at Smatch, which is a tool at least these days maintained by Dan Carpenter. It's really cool. It generates a bit too many false positive, but it's a really good tool to go and start inspecting where you could potentially be vulnerable. And yeah, it's still a work in progress. My best friend, Spectre v2. I spent a lot of time on that one. So what is? It's about training your branch predictor and to force the CPU to speculate on the predicted taken path. You stuff your branch predictor and then you jump there. So it's really interesting if you can start influencing the branch predictor in another exception level, in another privileged context. And once you can branch somewhere, you can branch to a variant 1 gadget. That's the obvious thing to do. And how's that possible? Well, it turns out that some CPUs do not fully tag their branch prediction by context. And what is a context? Is an exception level. What are you, user space, kernel space, or hypervisor? Could be tagged by ACID, which is the equivalent of the PCID on x86. So it's each process on ARM has an ACID. It can change over the lifetime of the process, but basically that tags a lot of information, including your TLBs and the virtual machine ID. So with that, you can precisely identify any memory access by exception level, process, virtual machine. And that works for branch prediction as well, except when you don't. A number of implementations only tag that branch prediction by PC and target. And these are virtual addresses. And if you can have aliasing across exception levels in terms of VS space, you're in trouble. So how do we mitigate Spectre v2? So the obvious way to do it is to invalidate the branch predictor in specific places. In the kernel, we do it between context switch plus a couple of other places so that you can't mess with the kernel itself. In KVM, we do that as soon as we exit the guest so that we can safely run the host. The trick is we need to do that without executing a single branch instruction. Otherwise, the guest can prime that branch predictor, and off we go. So let's invalidate the branch predictor. So on the R32, it's really easy. We have a branch prediction instruction, and that works nicely on at least 2 implementations. But actually, we don't mandate that the branch predictor is visible to software. So it's not, really. Which means it's legal to implement BPIO as an op. Too bad. So on R64, it's much clearer. It doesn't exist. So it's clearer. It's not necessarily good. We're in a bit of a bind here. So we have to do it in a non-architectural way. And it requires diving into the microarch and grabbing people having actually written the CPUs, talking to partners who have implemented their own CPUs, and finding out about things. A15, you set a chicken bit from secure mode, and then you invalidate the whole iCache. OK. On S57, you turn the MMU off and back on. On the S73, you have, from 64-bit mode, you have to switch to 32-bit and invalidate the branch predictor using the 32-bit instruction. It's cool. It's a nightmare if what you want to do is have a single kernel image that runs everywhere, and you don't want to litter the whole kernel with architecture-specific hacks. One thing to notice as well is that most implementations do not have microcode like on Intel. So how do we do that? I'm not going to make this 5 minutes. Sorry for lunch. So that doesn't scale. So one thing we can do is start abstracting things a tiny bit. So we don't have microcode, but we have firmware. So most implementations have what we call the secure mode. And so if you look here, it's tiny, and you could probably can't read it, but trust me. So the most privileged exception level is ER3, and that's where we stuff things like power management, secure service, things basically that you don't want to see in your operating system kernel. So you push things over there, and you have an API to call into those services. So the hypervisor can easily call into ER3 to execute something. There's only one implementation, Xgene, that doesn't have this feature. Well, tough. They can turn their branch predictor altogether. And yeah, we can't support these guys. So let's say that we're going to implement things at ER3. So dropping to ER3 on itself is pretty cheap. It's like taking an interrupt or doing a syscall. That's the same properties. But our SMC calling convention follows the procedure calling convention, which means you need to stash all the live registers that you would normally save if they are callee save registers. But we're coming from a guest. All the registers are live. And we need to save 18 of them. That all of a sudden, that's an overhead if you're really exit heavy. So let's rev it. Let's invent a new calling convention that only clubbers at most 4 registers, provide an SMC CC discovery so you can get the version, and we define some new architecture workarounds. Takes a bit of negotiation back and forth with people designing these things. But we got it implemented in the ARM trusted firmware. And each vendor can now provide their own architected way of invalidating the branch predictor. One thing to notice is if you don't have an implementation, you probably don't have a mitigation. Choose your vendor. So SMCCC Arch workaround 1. As you can guess from the 1, there's a 2. So it's implemented on top of that calling convention, and it's a system-wide service. And it allows the caller to find out whether, well, it's implemented, but also whether that particular CPU requires it. And that's because we support asymmetric configuration like big little. Panic. Yeah, big little strikes back. So the thing is, it's always safe to call that service on any CPU. It's just that it comes at the expense of performance if you don't require it. So how do we do that? So remember this invalidate thing before any branch. So it's quite a constraint. So we need that to be the first thing that happens as we exit. And it needs to be in the exception vector before we can branch anywhere else, because that's where we land. So that gives us 32 instructions on the 64-bit system. And we don't want that to impact non-affected CPUs on big little. So we introduce per CPU vectors. Instead of having one set of vectors that all the CPU uses, we introduce vectors for affected CPUs, vectors for non-affected CPUs. And so we have these non-affected CPU vectors, we call them canonical vectors, and one set for the affected CPU, so we invalidate, and then we branch. All good. And what about 32-bit? Do you really want to know? Terrifying. Though there's no good firmware story on 32-bit. 32-bit has a long history of embedded stuff where people run Linux in secure mode, so it's all a big mess. Fortunately, there's exactly two affected implementations. A15, which we've seen we can invalidate the cache, and A12 and A17, which despite having two names is exactly the same CPU, we can use BPIO. And we can use the same vector trick. And the trouble is we need to invalidate, do the invalidation and branch somewhere else in exactly one single instruction, and that's not going to happen. So, and that's terrifying. That's how we do it. So at the top here, we have the normal vectors. You know, it's a set of branches, 8 branches. The CPU drops you at the right position in the vectors. And that's here the way we hack things for affected CPUs. So the requirement is that we start with a 64-bit aligned stack. And we enter at any point here and fall through, adding 1 to the stack. Then we validate the branch predictor. At that point, we're safe. And here, we have a small, oh man, come back. Hello. Yes. What's happening? Wrong button, probably. Here, we have our decoding where we do an exclusive OR with that value here, which clears. We test that, oh, we found the right value. The bottom bits are 0. If it's not 0, we restore these bits by doing an exclusive OR again with the same value. And if it was 0, then we're good. We've aligned our stack back to a 64-bit boundary, and we can safely branch. Don't try this at home. If you do that with Thumb2, it's even more complicated. Look at the code. It's all in the kernel.
To subtract 1 step, since you added 1, now you can subtract 1 instead of doing the XOR.
That's much faster, because if you start subtracting 1, now I see what you mean. That would become a long string of conditional instruction. Yeah, you could do that as well. That could probably work as well. Thumb2 may be problematic. Yeah, I've removed half the code here. Had to fit. Fixing variant 2, really, we want to fix it for good. So it only exists because this lack of tagging in the CPU. So the architecture now outlaws that kind of behavior. Until now, you could build things like this. If you come up with a new CPU and you allow aliasing, you're out of spec. You're not an ARM implementation. We expose that fact into a system register, so hypervisors and OSs can read that system register and know whether they are protected or not. And we've updated, actually, a number of implementations to support this. Meltdown. That's going to be quick because, guess what? There's only one affected implementation in ARM, so you all know what that is now. Yeah. Not user accessible. Oh, look, it's accessible. How do we mitigate in KVM? Well, it's pretty nice because the guest run at EL0, KVM at EL2. Well, guest run at EL0, EL1, KVM at EL2. These are different translation regimes. They don't interact directly. So you can't exploit anything directly in KVM from the guest. It's the user space side you need to worry about, and that's protected by KPTI. And the only known implementation has been already addressed, so let's move on. Variant 3A. So that one's fun. It's vaguely similar to Meltdown in the sense that it allows the bypass of a privilege separation. And in this case, it's a system register, the equivalent of an MSR on the x86 side. So it sounds worse than it is, really, because most of the values you have in these system registers, they are static. They don't reveal anything. I mean, you can read VM Linux and find out what these values are. You can read the source code. The only thing that's interesting is the vector-based register, where you branch when you take an exception. And this one's interesting because it's a virtual address, which means you can disclose how your kernel is mapped in memory, which means you bypass things like KSLR. Annoying. Especially annoying for me because I was in the process of writing randomization of high virtual addresses. So this thing completely defeats 4 weeks of work. Don't do that. And of course, you can combine it with other things. And we know of 2 affected implementations, F57 and F72. So is that possible? Yeah, well, yes, we're speculating. We just return the data. It's okay. Always the same thing. So we've learned a few things from KPTI. Is that with KPTI, we set the vectors at a well-known location because the kernel is not mapped, but we still need to map our vectors so that we can take a page fault or an interrupt, for example. The good news is that doesn't disclose anything about the kernel layout. After all, that was the way we justified merging the KPTI patches in the first place. Oh, look, shiny, it fixes some potential disclosure on KSLR. And we can use the same trick. So the idea is we're going to ID map the vectors. Like basically, VA equals PA for the vectors. So that doesn't disclose anything about the hypervisor VA layout. And we can branch back to our known ID map vectors. And yeah, you said branch to the vectors. There was something about that. Yeah, that won't be a last question. I'm really sorry. If you want to leave by any means, I understand. Lunch has priority. So we need to branch from these vectors, these ID map vectors into the real ones, which is some random location. So our address space is about 52-bit, though on this CPU it's actually 48. And still, it's quite large. And our direct branches are PC relative, means our max displacement is 4 gig. That's not going to cut it in a 48-bit address space. So we must do an indirect branch after having mitigated V2. There are 2 possibilities. Either we load that target address from memory. That's cheap. Well, it's easy, but that's not cheap. That's not very efficient. Or we can patch the target address at runtime using a complicated series of immediate loads. And that's quite hard. So of course, if it's hard, we're going to do that. So much fun. And for that, we rely on alternative sequences. So far, we've had alternative sequences a bit like x86, where we say, OK, here's the canonical set of instructions, and we can replace them under some conditions with this other set of instruction. Here, it's a NOP that gets replaced with a branch if ARM64 has privileged access never. So for what we want to do here, we need that to be slightly more dynamic. And turns out we have a good way of generating dynamic stuff. We have BPF in the kernel. Great. Which means we have all kind of helpers to generate any encoding for any instruction. And we can basically patch our kernel. So let's use that to our advantage. And so here on the left, we have this new, slightly different version of an alternative, which is alternative CB for callback. Takes this. And this is a C function that is going to replace this branch and a series of NOP with a store to the stack, because we need to make some space, a move of some constants with the right shift installed in order to build a 48-bit address, and then an indirect branch. So all that gets computed at runtime and patched into the kernel. That works really well, actually. Surprising. But yeah, it's a lot of effort for one single register. But we've gained full randomization of the VS space, which is an interesting security feature, just in case we get some more of this. But thankfully, there's only 2 implementations affected. And then we have SSB, which is the last one I worked on, and frankly, I don't want to work on another one after that. Speculative store bypass. And the idea is that under speculation, a load from an address can observe the result of a store that is not the latest store at that address. So you do store 1 to address A, store 2 to address A, load from A, and you may get 1 under speculation. So in the kernel, the thing that really worries me is the way we use the stack. We do a syscall from user space. We store things on the stack. We process that, return to user space. And then at some other point later, in a completely unrelated context, we're going to reuse that stack frame for an entirely different purpose. And we're going to store something on the stack, read back from it. Oh, wait. Are we reading the right value or the one that's been generated by user space earlier? That bit is slightly frightening. And yeah, how's that possible? Speculation may ignore the dependency because you have a write buffer that doesn't forward things immediately, or you've used a different VA, for example. I mean, there's plenty of ways to build something that has this behavior. So at the time of the discovery, we didn't have anything to prevent that in the architecture. But all implementations had something that had a chicken bit similar to load bypass store disable. If you have a store in flight, you can't have a load that bypasses it. So that really guarantees that variant 4 cannot occur, but it affects all loads. So that's configurable from EL3, and if the overhead is minimal, if your core is not heavily speculating, if you don't rely massively on speculation to get all of your performance, then you set it from EL3 and you're done. Okay, you've disabled that, but you're safe forever. The alternative is to invent yet another secure service, this time workaround 2, which is enabled on entry from user space into the kernel, disabled on exit, and then we can have a buy-in mechanism where the process has to be mitigated. So that's mostly what x86 does, except that we always mitigate the kernel, always, always, always. On x86, you would enter the kernel not mitigated, set your PR CTR to be mitigated, and exit with the mitigation on. So how does it work? It's just like workaround 1, except that this time it has a state, enabled or disabled. So again, it's system-wide, but per CPU mitigation status. Again, big little. And we expose the mitigation to VMs. So the guest can change mitigation state at any point by calling into the hypervisor with the same workaround 2 call. And KVM forwards that to EL3 and has to keep track of that context tracking, of that context, which means that context becomes part of the mitigation state, of the migration state. So moving on with variant 4, because this thing is not going away. It's not easy to mitigate. But what we've done so far is that we've architected a way to actually enable, disable that feature without taking a trap. So now we have a p-state bit that we can set or clear. And we default to secure. So if you, by default, you boot with that bit set to 0, as in any revision of the architecture, and that feature is disabled. It now requires a buy-in from any exception level to enable it. So we save quite a lot of performance by simply not trapping. That's pretty good. And we've just merged the patches for that into 420. So as a conclusion, we've changed a lot of things in the way the kernel works and KVM works for ARM to cope with these Spectre mitigations, Joe. And we've had to introduce a number of abstractions. Effectively, we've moved part of the architecture into the firmware, because that's the only place where we could safely mitigate it without ending up with a massive complexity problem. That has taken months of really, really hard collaboration between architecture, implementations, firmware, and the kernel group at ARM. And we've managed to introduce mechanisms in the architecture to make sure it's a bit more manageable in the future. But still, it's been heavy. And on that, I thank you. And if you have questions.